Today we are gonna deep dive into a very crucial aspect. Like I guess most of you are at least familiar with a very breakthrough innovation in English. Okay, fine. We'll keep it in English only. A very breakthrough innovation which has happened some decades back by the name of neural networks. Neural networks सबको ही पता होगा, I guess. नहीं भी पता होगा, we'll have a short section. हम उसमें एक छोटा सा brief recap देखेंगे उसका, ठीक है? So this session is primarily focused on activation functions only. We'll see the development of activation function. कैसे हमने सबसे एक बहुत basic level से हमने start किया activation function को build करना from a very naive one like sigmoid function, and we'll see the different journeys of all. Like we'll try to cover most of them, but there are a few left. That is something for you to explore, to try out. So all set. A quick brief about me. I'm Sanjay Shrestha. I was an software development intern at G&D Educara, and I'm an AI/ML enthusiast, and also a pre-final year student at SRMU. A very short info. I'll just talk about what are neural network for folks जिन्हें idea नहीं है या फिर first time इनका introduction हो रहा है. Neural network is simply just a computational model. What we do is हमारे पास brain है. We know how a brain works. We try to simulate the response जैसे एक brain work करता है into some model upon which our data can you utilize to generate some output. Like जैसे हमारा brain, let's say if something hot is in front of you, हमने उसको छुआ, brain के पास input गया कि okay from the sensory organs कि okay like संजय इसने कुछ गर्म छुआ है, it generate वो hand के पास एक response generate करेगा कि ना, you just pull your hand back. So this was a simple information cycle. If you can scale it up on very complex phenomena, that's fine. But that's how naively a brain works. Like you have some sensors through which you get the input. It passes through the spine, your networks. In the neuron, you have the structure of neuron where dendrites takes it input, processes it, generates some output, goes back to your effectors muscle, and the response is triggered. Pretty simple, right? समझ में आया न्यूरल नेटवर्क क्या होता है? एकदम simple language में I just try to keep it very naive. All you're doing is you're trying to simulate what your brain does to some data into some computer. So they actually learn from example. You don't train them like एक बच्चा जैसे, as you see it growing, it learns from example, doing stuff, making mistake, correcting those mistakes again, and this is an iterative process. It goes on and goes on. So same way neural network works. What happens for every mistake they do, it like in brain there is we'll talk about more about the connections. Like if we in a brain, it consists of some neurons, right? Neurons में कुछ dendrites होते हैं. There are soma, there are synapses, there are myelin sheath. Synapses basically controls कि कोई response अगर brain को मिला है तो उस पर कितना emphasize करना है. The more better the connection is, the more better would be the response, right? Or it could just modify the synapses based on the responses. So what we are trying to do in neural network is we are trying to simulate what a neuron does. Like this is a simple perceptron, a single neuron. We connect it like brain में तो ऐसे बहुत सारे होते हैं. We have a network, a dense network of all of these, trying to simulate taking the input, doing some processing, and generating some output. This is a naive way to getting started with this. A typical neural network architecture, let's also discuss this. You have some inputs, like हमारे brain के पास हमारे eye से भी input जा रहा है, हमारे skin से भी input जा रहा है, हमारे tongue से भी जा रहा है, nose से भी जा रहा है, ear से जा रहा है, और भी बहुत सारे sensory unit हमारे पूरे body में. So you have a bunch of inputs which brain takes into account, which can be replicated into a input layer, जहाँ पे हमारे input को feed किया जाता है. Then you have some neurons, which are these blue ones and some green ones and some this purple one. These are some neurons. What these neurons does is take some input and do some processing. We'll just say कि we'll do some processing. कैसे processing करते हैं, कैसे what is the mathematics? We'll try to keep it थोड़ा सा not in this session, but हाँ, each neuron generates some output, which is further received by another neuron, and so on the processing goes, and you get a final output into this output layer. So from this architecture, you can see there is an input layer, there is an output layer, and in between, we have some layers which are sandwiched in between the input as well as the output layer, right? So within these, all of the computation, the important computation takes place. ये बहुत important है. Like these hidden layer are the primary, they are responsible for capturing everything out of your data. जो data में हमने दिया है, सारे complex pattern to identify करना, उस पर processing करना, these are only responsible. Along with this, for every neuron, you can see you have a bias and you have a corresponding weights. We'll discuss on this, but I guess itna clear ho gaya sabko. Should we proceed? Should we proceed? Give me a thumbs up if it makes sense. Fine. So I guess itna jinne bhi like nahi bhi like first time introduction hua, I guess this part was clear. So let me move forward with explaining the concept of non-linearity with chai. चाय हम सब बनाते हैं घर में, सबको पसंद भी होगा, राइट? I just let me know how many of you are from hostel, और कभी भी like अपने like इतने ईयर में हॉस्टल का एक्सपीरियंस हुआ हो, just raise your hand. I like to make it a bit interactive, थोड़ा सा. Fine. Just tell me कि हॉस्टल में जो चाय मिलती थी वो कैसी होती थी? Just tell me वो कैसी होती थी? Is it good? Is it bad? फेंक देते थे, देखना नहीं पसंद करते थे, क्या होता था? Just type it out so that I can understand. Or if somebody would like to say something, highly appreciable. Okay, Rashi says. Anshul, lots of water. मतलब, okay, fine. Chat after that. Okay, fine. So I guess just tell me if I'm not wrong. If you get a preference, अगर तुम्हें ऑप्शन मिले कि तुम्हें हॉस्टल का चाय और कहीं बाहर का चाय पीना है, I guess majority of us would believe कि हम बाहर वाला चाय को प्रेफरेंस देंगे rather than हॉस्टल का चाय. हो सकता है एक्सेप्शन हो, there are outliers, but in general हम बाहर का ही चाय प्रेफर करते थे. हाँ, in house, हाँ, like this is the general intuition कि हॉस्टल का चाय is not something we would appreciate. अगर हमें प्रेफरेंस मिले कि हमें बाहर का चाय पीना पड़े, हम बाहर का चाय पी लेंगे. Same is with the data set. The data is around in real life. These are not something very simple. Like अगर हम एक simple, if you have to make some chai, हमें क्या input चाहिए? We would need some milk, we would need some चाय पत्ती, we would need some पानी. अगर तुम्हें पानी वाला चाय, like I assume कि थोड़ा सा mix हम करते हैं, and we need some sugar. These are the input, right? Just tell me yes or no. Give me a thumbs up if it makes sense. These are the input we would need to make chai. Now ऐसा थोड़ी होता है कि हम चाय बनाते हैं तो जितना हमने चीनी डाला उतना ही हमने पानी डाला, उतना ही हमने चाय पत्ती डाला एंड सो ऑन, राइट? हमें क्वांटिटी डिफाइन करते हैं कि हाँ, इफ वी वांट टू मेक लेट्स से दूध वाली चाय, हम दूध को इतना ज्यादा इस प्रपोर्शन पे रखेंगे. इफ वी वांट टू मेक पानी वाली चाय, वी वांट टू मेक इट इन दिस प्रपोर्शन. सो यू हैव सम क्वांटिटी एसोसिएटेड विद इट, right? Like 1 tablespoon of chini, 50 ml of water, 2 teaspoon of chai patti, and 50 ml of milk, right? So these are what? These are your weights in your neural network. Just let me go here. You can see there are some numbers written in W1, W2, and W3. These are actually the weights. और ये बताता है कि एक पर्टिकुलर इनपुट एक आउटपुट जनरेट करने में कितना इंपॉर्टेंट रोल है, कितना सिग्निफिकेंस है उसका इन जनरल. इफ वी इंक्रीज the weight of milk, दूध जो चाय बनेगा हमारा वो ज्यादा like milky होगा. If we want to make the chai more like if you want to add more water, पानी वाला चाय बनाना है, you can increase the weight of water. अगर हमें बहुत ज्यादा like बोलते हैं ना कड़क चाय बनाना है, we can increase the amount of चाय पत्ती जो हम डालेंगे, right? Same way a neural network works. You have some input, हमने weights assign किया है, and we feed it into some processing. हम process कर रहे हैं कि okay, we are boiling it. Now the question comes कि ठीक है, हमने चाय तो बना दिया, अब चाय बनने के लिए भी we need a minimum threshold, we need a minimum temperature. हम सॉसपैन को अगर स्टोव पे रख देंगे तो सिर्फ उससे चाय नहीं बन जाएगा, right? We need a particular temperature जो हम बर्नर के नॉब से हम रेगुलेट करते हैं. कोई बोलता है कि ठीक है, मेरे को I want my tea थोड़ा टाइम लो बनाने में, 10 मिनट लो, 5 मिनट लो बनाने में. okay, we make it simmer, we let it infuse, होने रहता है. कुछ लोग होते हैं कि नहीं, I want my chai quick, full नॉक को हमने हाई मोड पे रख दिया, नाउ कड़क चाय एकदम धड़क रहा है, बॉईल हो रहा है. So how you want your output, this bias term actually influences it. It sets out the minimum, एक minimum threshold define करता है कि okay, if you want to make a tea, you need a minimum this much temperature so that हमारा process शुरू हो पाएगा. Same way in neurons, these biases actually triggers कि अच्छा इस input के लिए, इतना input के लिए हमारा neuron activate होगा. And this is the simple hostel वाला चाय कि भैया simple कुछ हमने ऐड नहीं किया, बस इसी को process कर दिया and you get a chai. Now, just tell me, क्या ऐसा चाय कोई पसंद करेगा? Like अगर उसे preference मिले, let's talk 3 questions. Will this chai taste good? हो सकता है किसी को पसंद आए, but in general कोई ऐसा चाय पसंद नहीं करेगा. Like if somebody is really into chai, nobody would like it. हो सकता है there would be some exceptions, but in general nobody would like it. Now, is this how we generally make the chai in real life? नहीं, right? हम रियल लाइफ में चाय बनाते हैं, हम उसमें कुछ लोग अदरक डालते हैं, कुछ लोग इलायची डालते हैं, कुछ लोग लौंग डालते हैं, and there are some other spices which people add. ये क्यों हम डालते हैं? We add it so that it could add the depth to the flavor. एक simple, एक plain चाय हमें नहीं पसंद है. We want some complex, aromatic चाय. स्मेल करे मजा आ जाए, जो हम लोग बोलते हैं एकदम कड़क चाय बना है, मजा आ गया, right? Same way in real life, your data are not simple. जिस डेटा पे हम अपना प्रोसेसिंग करेंगे, जो डेटा पे हम कंप्यूटेशन करना चाहेंगे, these are not simple stuff. बहुत सारे फीचर्स होते हैं, बहुत सारे कॉम्प्लेक्स फीचर्स होते हैं. So we need something to actually take into account of this complexity. So how do we do it? Let's take the same analogy, but with a twist. Now we are adding spices. Same other stuff are there कि हमने मिल्क लिया, चाय पत्ती लिया, पानी लिया, शुगर लिया, and we are adding some spices. ठीक है, जिसको जो स्पाइस का जो क्वांटिटी रखना है रखो. We put it in saucepan. हमने 22 डिफाइन किया, अच्छा we want, ठीक है, मीडियम फ्लेम पे बनाओ चाय. Now what happens is, चाय तुम्हारे पास बॉईल होके we get some boiled liquid, बॉईल तो हो रहा है. Now what we want is boiled liquid. तो हमें I could just show it here. एक हमारे पास boiled liquid तो यहाँ भी पड़ा हुआ है, ये भी एक बॉइल्ड लिक्विड है, बट इसमें उतना अरोमा नहीं है, इसमें उतने कॉम्प्लेक्स टेस्ट नहीं है, कॉम्प्लेक्स फ्लेवर्स नहीं है. तो वी नीड अ प्रोसेस जो इस बॉइल्ड मिक्सचर को एक्चुअली ब्रू कर पाए, सो दैट जो भी जो स्पाइसेस में फ्लेवर्स है, जो भी चाय पत्ती में जो फ्लेवर्स इन्फ्यूज होते हैं, वो एक्चुअली हमारे चाय में आए, सो दैट वी कैन एक्चुअली अप्रिशिएट कि भाई हाँ चाय अच्छा बना है. लाइक हम जो बोलते हैं अच्छा चाय बना है किसी ने, अदरवाइज हॉस्टल वाले लोग जान रहे चाय कैसा होता है. सो दैट हाँ, and also we have to make sure कि जो complex flavors हमें अलग अलग ingredients आ रहे हैं, उनको हम balance कर पाए, so that we can get a कड़क चाय ultimately. So these stuffs are not very simple and linear कि भाई हमने बस डाला और वो boil किया और हमें मिल गया चाय. ऐसे चाय नहीं होता है ना, right? If you're really a chai enthusiast, you want it brewed, you want it infused with the spices and other stuff. So this is actually a complex thing. You have to analyze the input to get the complex flavors, और उसको भी एकदम correct proportion में हमें infuse करना है, so that we can get the कड़क चाय we all love. Make sense इतना? Make sense इतना? Give me a thumbs up if it makes sense right now. ठीक है? Perfect. Now what happens is, same happens with a data set. In real life, the data is very complex, and it is not linear, by the way. कि हमने सिंपल वी कैन मेक सम लीनियर फंक्शन कि हाँ इस फंक्शन में अगर हम ये इनपुट डालें और हमारा चाय बन गया. लाइक एग्जांपल, अगर मैं लेट्स से अगर मेरे को स्ट्रॉन्ग चाय बनानी है, अगर मैं चाय पत्ती को 2 टेबलस्पून से डबल कर दूं, तो जरूरी थोड़ी है कि मेरा जितना स्ट्रेंथ होगा चाय का वो डबल हो जाए, सीधे डबल. या फिर इफ आई इंक्रीज लेट्स से द क्वांटिटी ऑफ स्पाइसेस, मेरा अरोमा उतना नंबर ऑफ टाइम्स इंक्रीज कर जाए. नहीं होता है ऐसा. देयर इज सम कॉम्प्लेक्स रिलेशनशिप बिटवीन द वेरियस इनपुट्स एंड द आउटपुट यू गेट. So we need something which could actually map this complexity. So that is why that is where the activation function comes in. This activation function takes into care कि तुम्हारा डेटा सेट जो तुम इनपुट में दे रहे हो, जो भी तुमने डेटा दिया है इनपुट में, उससे जो भी कॉम्प्लेक्स फीचर्स है, it will extract it, and based on that complex feature it will generate some good output. as compared to the simple linear one. So simply, what is an activation function? I guess मैंने एक background set कर दिया कि activation क्या होता है और क्यों जरूरी था. Like simple, it is just a mathematical function which is applied to the output of every neuron. Let me go back. You can see for every neuron, you can see there is a Z and an F. I talk about this. This Z is a linear target function जो सबको सारे input को sum up कर रहा है, weighted sum निकाल रहा है. And this F is actually an activation function. For every neuron, it is defined. Or you can see this is defined for the output which is coming from the previous neuron. Perfect. So this does what? It transforms the input which you are getting so that it could be easily processed by the next layer. Now the question comes कि भाई हमें जरूरत क्यों पड़ी? जैसे मैंने चाय में बताया है, it introduces non-linearity to the network to capture complex relationship. चाय में भी हमने देखा we need some processing जिसमें हम infuse कर पाए flavors को, infuse कर पाए aroma को एक correct proportion में, right? क्योंकि चाय एकदम simple बस add किया, boil किया और हमें चाय मिल गया, वो चाय नहीं होती है real life. Right? Same goes with this activation function. That is the problem which activation function solve. For example, I can have a classification problem, let's say, and I can have a linear decision boundary. And I'm taking this on hypothetical case. कि हाँ, इस linear boundary के ऊपर में जो भी हमें ये dots मिल रहे हैं, this goes into the category of this circle, और इस decision boundary के नीचे जो हमें point मिल रहे हैं, cross का वो classification हो. But in real life जरूरी एकदम ऐसा you can get a straight and a linear classification line. जरूरी ऐसा. If we are talking about multiple dimension, क्या हमें जरूरी है कि हमें एक hyperplane मिल पाए? कि हम उससे classify कर पाए कि अच्छा anything above this is a category and anything below this is another category. Real life में ऐसा नहीं होता. You can have a very complex function which could actually define the relationship. हो सकता है वो एक यहाँ पे मैंने एक circle से denote किया, it could be some quadratic function, it could be some other function, but it would not be a linear function. जरूरी नहीं है कि वो linear हो. So for that, you would need this activation function so that it would help you build a hierarchy of features. जैसे जैसे अलग अलग layers में हम जाते जाएंगे, एक एक feature extract करते जाएगा and it goes on. I guess activation function क्या होता है, क्यों जरूरी है? I guess this part was clear from my side. Is it? Give me a thumbs up if it makes sense. Perfect. Let's hop on to the types and use cases and various limitations. So activation function ना, जैसे हमने बताया कि एक न्यूरॉन के आउटपुट के बाद हम यूज करते हैं, राइट? फाइन. तो हम अगर मैं आर्किटेक्चर बताऊं, आर्किटेक्चर में वी वर बेसिकली इंटरेस्टेड इन हिडन लेयर्स एज वेल एज इन आउटपुट लेयर. तो एक्टिवेशन फंक्शन कहाँ हम लगाते हैं? तो यू कैन मेक अ कैटेगरी ऑफ टू. यू कैन हैव एक्टिवेशन फंक्शन जो हम हिडन लेयर्स में लगा सकते हैं. वी कैन हैव एक्टिवेशन फंक्शन जो हम आउटपुट लेयर्स में हम लगा सकते हैं. These are some examples like Sigmoid, TANH, ReLU. We'll come one by one to this. But in output layer, we have some specific ones only. ऐसा नहीं है कि hidden layers में हम सारे जो hidden layer में use कर सकते हैं वही सारे हम output layer में लगा सकते हैं. नहीं, ऐसा नहीं. Like you can also have an output layer with no activation, linear activation. Agar if you are working with regression problem, we don't need something as a very specific like sigmoid or softmax as an output activation function. जरूरी नहीं है ऐसा हो रहा. So there could be a chance जहाँ पे activation function नहीं भी हो output layer में, but hidden layers में there is a chance. So let's start with a very naive one, which is a sigmoid function, which is given by this formula. Sigmoid of x is given by 1 over 1 plus e raised to the power minus x. Up, let's do not focus on the text. Let's see the graph. You can see the graph of sigmoid function something like this, right? Something like this. This function, as it crosses 0, it is approaching to 1, and as it goes negative, it is approaching to 0. और यहाँ पे कहीं 0, like at exactly 0, ये function है 0.5. So just imagine if we have a case जहाँ पे हमें data को classify करना है 0 and 1 में. Like we can have a class 0 and we can have a class 1. So any data which is positive, just a second. Any data which is positive will take a value close to 1. And any data which is negative will take a value which is close to 0. So कोई भी अगर x हमें ऐसा मिले जो positive values के लिए defined हो, तो I can put it in some category 1, and if it is defined for a negative value, I can put it in some category 0. So this is a classic example of binary classification, जहाँ हमें दो classes में सिर्फ classify करना है हमारे data set को. Like use cases you can see, we can simply use it in binary classification, जहाँ पे हमें output 1 और 0 के बीच चाहिए. We can have a class 1, which can have a class 0. Here we have a threshold of 0.5, so we can say कि अच्छा कोई भी data set है, उसके लिए अगर sigmoid function का value 0.5 से above है, it belongs to category 1, and if it is defined for anything less than 0.5, it is belonging to class 0. So this is a very naive one to start with, as an no, you cannot make it in multi-class. We'll come on that. See, that is exactly the problem is with this function. यही problem है कि इसका range limited है 0 to 1 के बीच, right? 0 से 1 के बीच we are defining its range. So we cannot ideally use it for a multi-class classification. Moreover, this has a very peculiar problem, which is known as vanishing gradient problem. Okay, so for this, let us see in the curve, you have a purple bell curve. एक purple bell curve यहाँ दिख रहा होगा, right? This is the derivative of this sigmoid function. क्योंकि जब भी हमें gradient, जब भी we want to get the best value, we want to calculate some gradient. We actually use gradient descent to be very precise. Like उसके भी अलग-अलग variant होते हैं, right? But in general, we have this gradient. We want to compute the derivative. Now, what happens is, as you can see, for values greater than, like say 0, the gradient value is very less, close to 0. We have for, let's say if the value is 0, the gradient is about 0.25. That is the maximum value. So anything you multiply with this gradient, it would appreciably come down to a very small number. Right? अगर हम let's say कि 0.02 को multiply करते हैं, sorry 0.001 को multiply करते हैं एक और number से, so it would come down to a very small number. And let's say कि we have another parameter which is actually a learning parameter, which is also in the range of let's say 0.01 or something in that range. So the final number आपके पास आएगा, it would be very small. So what happens is, this gradient will sooner approach to 0, and your learning will significantly come down. जो हम updation करना चाहते हैं अपने parameter में, over the time, वो learning हो नहीं पाएगा, वो updation हो नहीं पाएगा, because your gradient is actually approaching 0, or if not 0, then a very small number. So these are the two problems which are with this sigmoid function. So ये problem जब आया, then we got to think, okay, let's try to look for some other solution. Do we have some other function? Yes, we have some other function, which is known as hyperbolic tangent function, or arctan function, somebody would say, or somebody would like to say tanh function, which is given by this formula. Now what happens is, with this function, you can actually sandwich your data, or you can squeeze your data between a range of -1 and 0. You can squeeze your data in between -1 and 0. Like in the case of sigmoid function, you have the range of 0 to 1. Now you can extend the domain from -1 to 1. Sorry, the range from -1 to 1. थोड़ा सा और flexibility हमें मिल गया. Right? So you can actually use it in some regression problem, जहाँ पे you want some data in between this range, or even some classification where the data is centered about 0. This is a very important concept कि हमारा data should be centered about 0, which is not in case with sigmoid function. Now you can, to generate some zero-centered output. Zero-centered output means if you take all the output and you take this average, you will get 0. The mean is around 0. So with this thing also, you have some problem. Vanishing gradient, it would remain same, like as you can see, as we increase on the x-axis, increase on the values of x, the gradient actually comes down to a very small number, and effectively it will approach to 0. So for very small gradient, you will not be able to update the parameters as you want. right? And same goes with the range. हमारा range सिर्फ -1 से 1 के बीच में है. So if you want anything which the values goes outside this range, वहां हम इसको use नहीं कर सकते. Moreover, do we have some other solution to this? Yes, we have. We have a very prominent activation function which is known as rectified linear unit, ReLU. कितने लोग हैं यहाँ पे जिन्होंने इसका नाम सुना हुआ है? Just raise your hand if you know something or if you have heard of this term. Fine, fine. So we have few folks जिन्होंने perfect. Kindly lower your hand. Okay, जो लोग नहीं जानते, ठीक है, I'll discuss this. So जो problem हमारे पास आ रहा था with sigmoid function, with arctan function, this ReLU function has tried to address it. How? Let's see. So here you can see, first of all, let's see how it is defined. So this function is defined for only positive value, including 0. So for all values which is greater than 0, it is simply x. And for every other value which is not 0, means simply the negative values, this function is 0. So this function goes something like this, and at 0, it has a very strong corner and it shoots up linearly. Okay, you have a good function, jahan pe hamare paas we have a lower limit of 0 and it can extend to a good value of x as we increase x. Fine. So what happens is, okay, we have a greater value point, so we can have a greater scope to actually capture data, actually capture complex patterns. So is it the best one? The answer is no, it is not, because it has some serious problems associated with it. But okay, let's want to get into that. Just see from this graph, for all value which is not positive, that means all the negative values, this function is actually 0, right? Make sense? दिख रहा है सबको? अगर हमारा value negative है, तो ये function का value is 0. तो इससे problem क्या आ रही है? तो problem इससे ये आ रही है a specific condition which is known as dying ReLU or dead neuron problem. What it is? If for all negative value of x, the output is actually 0. So basically, your neuron is not functioning. The output is 0 from this function neuron. So it is technically a dead neuron. So what would happen is, over the period of like in the deep neural network, if various many of them neurons are not working, or you can say they're in their dead state, it actually affects the parameterization of let's say weights or biases which we do while back propagation. So we also don't want that. Moreover, you can see for all the values which are greater than x, it shoots up linearly. तो हो सकता है कोई हमारे पास बहुत बड़ा वैल्यू हो x के लिए, तो उसके लिए हमारे पास ReLU का वैल्यू भी बहुत बड़ा होगा. Is it a good thing or a bad thing? Just let me know. Just poll. Just tell me, is it a good thing or a bad thing to have a very high output? Just type it out. Is it a good stuff? It is a problem, or is it is a benefit that we can have a greater value? Just type it out. Let's see. What I said, okay, Janvi said it is not good. Ujjwal says demerit. Fine. So I got it. So it is a demerit. Why? Because okay. So the problem is this, that for very high value of x, maybe it will create some bias. Okay, but the thing is, it will actually make your model more complex. And maybe the chances are that over the period of time, हो सकता है कि आपका जो वैल्यू आए वो आप एक्सपेक्ट ना करो. You can exceed what you want. अगर मैंने एक रेंज डिफाइन किया कि okay, I want the values in between this range, maybe your model could exceed it, right? So these are some of the problems, which is like you don't have a upper bound to this function. So do we have something better than this? Okay, if this is the problem, क्या हम इसको किसी तरह से solve कर सकते हैं? Yes, we can do it by different variants of ReLU. Like you have leaky ReLU, which is defined by this function. It is x if it is greater than 0, and if it is a negative value, it is 0.01 times x. You have ELU, which is exponential linear unit. you have x. If x is greater than 0, and if it is a negative number, it is given by some parameter alpha times e raised to the power x minus 1. Then you have CELU, which is defined by lambda times x if it is greater than 0, or lambda times alpha e raised to the power z minus 1 otherwise. Okay. Now the question comes कि अच्छा ये कौन सा problem को solve कर पा रहा है? So this leaky ReLU is able to prevent dead neuron because let me show this curve. Let's say if this is your ReLU function, 0 for all negative value and shoots up like this. So you have a bound below. यहाँ 0 से नीचे value नहीं जा पाएगी हमारी. If we talk about leaky ReLU, it is not bounded below. थोड़ा सा हम स्पेस दे रहे हैं कि this function can also attain some values if it is negative. So your neuron will effectively not be dead while training. Then you have exponential linear unit, which is also bounded below, but you don't have that corner at the you don't have a very strong corner. So this function is actually differentiable. It is smooth. Unlike this ReLU, which is non-differentiable at x is equals to 0. Then you have CELU function, which is this one. So I assume this part was clear. You can read more of it since we have a very less time remaining. I'll speed up thoda sa.
Just to add, really good going. जो पीछे वाली स्लाइड थी उसमें दो चीज़ें बताई तुमने, ग्रेडियंट एक्सप्लोडिंग एंड ग्रेडियंट वैनिशिंग, दोनों का नाम.
I didn't discuss the exploding problem.
So when you're
I just talked about it.
Yeah, when you're oh, you are going to talk about it.
Yeah, sure.
Okay, sure. Then continue.
Now comes a very important function, I guess, softmax function. This is very if I'm not wrong, even in your GPTs, this is the function which is used as an activation function in your output layer, if I'm not wrong. Why? कुछ तो ऐसा बात होगा इस function में. As I guess somebody has pointed out, we need something for Adarsh Tiwari has pointed out, we need something for multi-class classification. We need something जहाँ पे हम बहुत सारे categories में data को हम classify कर पाए. We need some such function. So this softmax function is a very important function. How? Because what it does is, for a given data set, for a given data point, it converts the data into a probability distribution. Okay, the probability of this 1.3 to belong to a particular category is, let's say, 0.02. The probability of 5.1 to belong to a category is 0.90. So you have a probability distribution which sums up to 1. अगर हम सबका sum निकाले, so it would be 1. You can actually use this probability to see कि अच्छा जिसका सबसे highest probability आया for a particular class, straight away वो particular data उस class से belong करेगा. So this function, if I plot it, like the formula is given by this e raised to the power zi over the summation of all zi's. So if I plot this function goes something like this. This is also having a threshold of around 0.5 somewhere, and as you can see, as the value approaches more and more positive value, it saturates to 1, and so goes for the negative value. Fine. So these are some of the various very commonly used activation functions. Do we have something? इसके अलावा कुछ है हमारे पास? We have a lot of functions. There comes a very important function, activation function, which was actually developed by Google Brains, which is known as SWIS, which stands for a self-gated activation function. We are going to discuss this very important function. So what was happening is, with ReLU, the ReLU function, as you can see, it was unbounded above and bounded below. Remember this term which I'm using. It is unbounded above, like for the positive values, and it is bounded below. Moreover, this function was monotonous. Like you can see, we can have an increasing curve or we have a no curve at all, no gradient at all. This function was also non-differentiable at point 0. So there were few issues with ReLUs which we needed to tackle. So that is why we had this another function which is known as Swiss, which tackled this problem using self-gating mechanism. I guess those who are familiar with LRUs or RNNs or some LSTMs, they know about gating mechanism, जहाँ पे हम output को input को gate करते हैं to dynamically modify the output. This was the same principle which was used with this Swiss activation function. So we had this gating, a self-gating mechanism whereby we determined how much of the input we needed so that we could get some particular output. What it meant कि अगर हमें कोई output चाहिए तो हम वो output grasp करने के लिए input को कितना change करें और कितना हम flow करने दें in the network. So it was given by this formula Swiss of x. It is given by x times your sigmoid of x. Sigmoid of x is your simple sigmoid function. So you have a multiplicative term here, x. If we try to plot this curve looks something like this, one in the red figure, something like this. Right? So if we talk about the properties, it was non-monotonic in nature. Unlike ReLUs and sigmoid, this function is non-monotonic. अच्छा, तो इससे फायदा क्या होगा? अगर ये non-monotonic है, तो इससे हमें क्या? हमारे मॉडल को क्या है? Exactly this non-monotonic nature allows this activation function to grasp, to identify very complex pattern out of your data set. तो हो सकता है ऐसा कोई चांस बने जहां पे ReLU फेल कर जाए because it is monotonous. There, this we'll actually show it. This Swiss activation function performs better, or if not better, at least comparable to this ReLU. Moreover, this function is also smooth. You can see, you can calculate the derivative at every point. Unlike ReLU, you cannot calculate the gradient at point x is equals to 0. This is not differentiable at here. Here we have a corner, but you have a smooth curve. So since it is smooth, what you can do? Since it is smooth, you can actually improve the learning rate. You can actually improve the learning of the, let's say, network where you are using this Swiss. So what happens is you don't have the problem of vanishing gradient. You will not be defined with a gradient which is actually 0 or very close to 0. So this problem of vanishing gradient is addressed by this activation function. Are we clear with this? I'll answer the queries in the last, but can we just keep the question for the last, Mayank sir?
Okay, cool. Thanks.
Perfect. Let's discuss some of the properties. We'll like as you can see, this is simply an output landscape for the different activation. For like if you're using some linear function like simple f is equals to f of x is equals to x simple, you get an output landscape which looks something like this. You have some strong patterns you can see. Could we take some real life examples? We'll come to this. We'll come to this. As you can see, if we plot this scalar function here, let's compare it with ReLU, right? So with ReLU, you can see you have this asterisk pattern. एक asterisk तरह का symbol दिख रहा होगा यहाँ पे, denoted with some gradient of red. These are some corners. These are some of the corners which ReLU have because of its monotonicity and its non-smooth nature. And we don't want that at all. We don't want it at all. Because what happens is this smoothing, the more smooth this landscape it actually affects how smooth your loss function is. Because the more smooth your loss landscape would be, it would be very easy to traverse and very easy to actually optimize it for your, let's say, learning rates. So this is a very ideal case as compared to your ReLU, right? Let's We also did some experimentation to actually see कि अच्छा, if these are all we have it in theoretical landscape, can we actually run some experiments and see कि हाँ क्या ये actually जैसा हमने सोचा है क्या ऐसे run करता है? Yes, it does, because let's see, it improves the training of your deep networks. Let's say we have a network in which, as we increase the number of layers and try to find out the accuracy for, this was done for MNIST dataset, which is actually for your digit classification. As you can see, with ReLU, since we are increasing the number of layers, your accuracy is going down and down and down. So if you're trying to build some deep networks, which a lot of layers in between, lots of nodes in between, ReLU is something we should not be going with, because as we increase the number of layers, we are actually facing the issue of decrement in the accuracy. We don't want that. So if we compare it with Swiss, okay, this is comparatively better. Okay, yes, we have some issues with we have some decreasing accuracy, but it is significantly higher than what ReLU is doing. We have tried to put it against batches, like we have did some batch normalization with CIPAR 10 data set, and we have tried to plot the accuracy again. And there also we have seen that ReLU is performing significantly poorer than what Swiss is doing. So similarly, we have other benchmarks also. So in general, we have seen that Swiss actually outperforms ReLU, and in some case, it is comparable to ReLU. Right? Makes sense. We have also tried it using ResNet 32. There also the same pattern was identified. So we can come to this conclusion that okay, yes, Swiss is actually outperforming this ReLU on various benchmarks we are setting. Is it possible that हम इसको एक ही डेटा सेट पे कंपेयर करें for some other activation function? Can we do it? Yes, we have done, and we have tried to benchmark it against another activation function. So for CIPAR 10 data set, we have different model, ResNet, WRN, DenseNet. We have different activation functions. Like as you can see, this Swiss is actually on the higher side. For CIPAR 100, you can also see this Swiss is actually performing better than other activation functions which are defined classically. We have used it on ImageNet also and tried to find out the top 1% accuracy over 3 different runs. So there also, this Swiss is actually performing much better than your ReLU. We have one more one more modification of Swiss, which is using some parameters. We'll not go into that, but yes, it is performing even better than Swiss. So that's all, folks, from my side. Let's have some questions. If you have, kindly raise your hand so that we can take some answers. What was the beta value? What was the beta? Beta value is simply your a parameter. It is simply a parameter you want because there is one more modification, which I said we'll not talk about that, where we have a parameter beta, which actually, if for that function which you have wrote, if you keep this beta as 0, your function is typically what? Your function would be a linear function. But if you try to put this beta somewhere close to infinity, your function, your Swiss function will behave like a ReLU function. So basically what you're doing is with this parameter beta, which is a trainable parameter, of course, we are trying to interpolate this function between a linear function and a ReLU function, which by calculating, by controlling this beta. I guess that answers it. Can we, I'm good for question. Do we have other questions or any feedback or something?
Great session, Sanjay. We have 10 to 20 minutes for question answer session. Anyone want to ask?
I would like,
Yeah,
if anyone would like to put up their own view, I'm also uh, open to that. Do we have some questions? What are some of the possible? Okay, we have one. We have Janvi says, what are some of the possible downsides of twist? Okay, so see, uh, let's talk about a deep neural network first. So in deep neural network, since we are calculating this sigmoid function and multiplying it with this x, this is actually computationally very complex. If we try to imagine it for a very large model, right? Moreover, let's say ki, for the like one point which mindset has asked, we have a beta value which is a trainable parameter. What if you choose some very poor beta? You choose some very poor beta value. What will happen in that case? So your model will actually become unstable because we don't want it. We don't want beta to be very close to zero because in that case it would be a linear function, and we don't want it to be tending to infinity because in that case it would be a ReLU function. So your choice would be a very crucial thing. Moreover, since this function is not monotonically increasing, your optimization would be a bit difficult because हो सकता है कि तुम्हारा gradient हमेशा, like when we are calculating gradients to actually optimize some parameter, we actually want that the flow or the direction of this gradient should be toward the global minimum. हो सकता है कि ये ऐसा non monotonicity के कारण ऐसा ना हो. We don't come to the global minimum, which is exactly what exploding gradient is. The steps you are taking to come down to this global minima, हो सकता है कि वो step enough नहीं हो, तुम overshoot कर जाओ वापस से from the global minima. So what would happen is ultimately you would over the number of iterations which you are doing, हो सकता है कि तुम global minima में कभी पहुंच ही नहीं पाओ for the correct or the least value you want. Right? So these are some of the drawbacks, or if not drawbacks, some of the downsides of Swiss. Do we have some other questions? I would be happy to. Uh, uh, how does ReLU function compares to other activation functions? See, in what aspect you want? Like if you want to simply do some sigma, like binary classification, and if you don't want some computation, you don't want it to be very computationally expensive. If you don't have a very deep neural network, use your simple function will work great. But since you have asked this question, I don't know in what context you are asking, but let me simply go back to this graph where if these are the problems which you are facing, हो सकता है कि आपके model में उज्जवल, I don't know in what context you have asked, but in general, if I'm talking, there are some problems with these simple activation functions. That is why we came up with some other function like ReLU, which is by far, if I'm not wrong, one of the most used one of the most popular one. If you try to ignore this problem, tying ReLU or unbounded output, it works very well as compared to other, let's say, arctan function or sigmoid function. Like you can see in arctan function, this function actually squeezes your data in the range of -1 to 1. And if you don't want that in your model, preferably you should not go with this one. With this also, you can see as the value goes increasing, this curve gets saturated to 1 and -1. So over the time, if you try to calculate the gradient there, it would be very small, and overall your learning would be hindered. And we don't want that. So these are some of the problems which ReLU has actually tried to solve it, but इसमें भी कुछ दिक्कतें थी. You can see over the if you try to calculate the derivative here, it is essentially zero or a very small value, and over the period of time your gradient will become very close to zero. Okay, fine. We have this paper. Something like this. Can okay. Thank you, sir, Mayank sir, for this. We'll definitely look on this.
Yeah, it
So yeah.
recently came out. Okay, just wanted to add कि
Yeah.
yeah.
If
Sanjay.
sir.
Yeah, Sanjay, please continue.
No, sir. Over to you.
Yeah.
That's it from my side.
या सो जस्ट वांटेड टू ऐड कि मेनली फंक्शन जो है दो तरह के हम कैटेगराइज कर सकते हैं। जैसे एक जो फंक्शन है वो हम हिडन लेयर्स के बीच में लगा रहे हैं। क्यों लगा रहे हैं? क्योंकि हम उनमें फ़ीचर्स फाइंड करना चाह रहे हैं, फीचर इंजीनियरिंग ऑटोमेटिकली करना चाह रहे हैं। तो जो लोग मतलब क्लासिकल एमएल मॉडल यूज़ करते होंगे, जैसे ग्रेडियंट बूस्टिंग हो गया या फिर तुम्हारा लाइट जीबीएम हो गया, उसमें क्या होता था, हम लोग फीचर इंजीनियरिंग मैनुअली थोड़ा बहुत करते थे कि फ़ीचर निकाल के उसको हम फिर दे रहे हैं, राइट। बट यहाँ पे डीप लर्निंग में हम फीचर इंजीनियरिंग अपने आप नहीं करते हैं। हम वी गिव इट टू द नेटवर्क कि भाई हम बहुत आलसी हैं, अपने आप फाइंड कर लो। तो वो कहाँ, वो जो ये फंक्शन है ये हम बीच में हिडन लेयर में लगाते हैं कि इसमें नॉन लीनियरिटी फाइंड करो, फीचर इंजीनियरिंग करो, राइट। और जो लास्ट लेयर होती है, ठीक है, वहाँ पे हम जो है कुछ फंक्शन लगाते हैं जहाँ पे हमें ये करना होता है कि जो हमारा आउटपुट है उसको हम किस रेंज में मैप करें, ठीक है। तो देर आर two categories. I think I missed this slide. You already added this. Okay, great. तो ये वाला, और दूसरी चीज़ एक ऐड करना चाह रहे थे हम कि जैसे सृंजय ने बीच में बताया था कि इमेजिन करो कि तुम्हारा ग्रेडियंट बहुत बड़ा हो गया, वैल्यू बहुत बड़ी हो गई, तो क्या इशू होगा, बड़ा होना चाहिए कि नहीं होना चाहिए, राइट। तो अभी कई लोगों ने बोला था कि इशू होगा बड़े होने से। तो वो उसी लिए उसी के अंदर ये प्रॉब्लम आती है ग्रेडियंट एक्सप्लोडिंग की, ठीक है। कि हमारा अगर ग्रेडियंट बहुत बड़ा हो जा रहा है तो वो एक्सप्लोड हो जाएगा, ठीक है। और अगर बहुत छोटा है, ठीक है, तो वो वैनिश हो जाएगा। सिंपल प्रॉब्लम। अब यहाँ पे थोड़ा सा पीछे जाते हैं कि कई लोगों को ये कन्फ्यूज़न होगा कि पूरा पार्ट पढ़ा दिया बट ग्रेडियंट है क्या, ठीक है। तो ग्रेडियंट बेसिकली नथिंग बट इट्स जस्ट द रेट ऑफ चेंज, ठीक है। जो आप मतलब जैसे आप घर में आपके जीने होंगे, ठीक है, घर ऊपर छत पे जाने के लिए, तो आप देख रहे होगे जितना ऊपर जा रहे हो उतना उधर भी ऊपर जा रहे हो, रेट ऑफ चेंज आपका हो रहा है, राइट। तो बेसिकली इट्स जस्ट अ रेट ऑफ चेंज कि आप इनपुट कितना दे रहे हो और आपको आउटपुट कितना चेंज हो रहा है उस पर, ठीक है। आप एक इमेजिन करो, एक जैसे वो देखा है डीजे डीजे मशीन देखी होगी, राइट। तो उसमें हम बास या टेबल या जो भी रॉक हमारा पॉप रहता है उसको थोड़ा सा इधर उधर करते हैं, कई सारी बटनें होती हैं ना उसमें, हम थोड़ा सा इधर उधर करते हैं तो वो म्यूज़िक जो है काफ़ी चेंज होता जाता है, ठीक है। बहुत सारा चेंज है, ऑडियो विजुलाइज़र देखा होगा, थोड़ा सा चेंज करो काफ़ी हो जाता है। तो सेम लाइक दैट कि हमारा इनपुट है, हमारा एक्टिवेशन फंक्शन है, कई सारी चीज़ें हैं इसमें, वो हम कैसे चेंज कर रहे हैं और आउटपुट हमारा कैसे चेंज हो रहा है। अब मॉडल को ये सारी चीज़ें पता करनी है। और जो हमारा मैट्रिक्स है, बेसिकली ये जो न्यूरल नेटवर्क है इसके अंदर में हमें कुछ बड़ा सा चीज़ नहीं होता है, एक मैट्रिक्स ही होता है, हमें वो ट्यून करना है, ठीक है। तो मॉडल सारे पैतरे अपना लेता है सामदान दंड में कि हाँ इधर से ये जाना है, इधर से ये कौन सा मैच करेगा, कितना वैल्यू मैच करेगा, उसके लिए वो सारे वैल्यूज़ को ट्राई करता है। और जिधर भी हमें ये पता चल जाता है कि हाँ वैल्यू हमारी अप्रोच हो रही है जीरो के करीब, कि मतलब हमारा जो लॉस है वो जीरो जा रहा है, तो हम मतलब सही दिशा में जा रहे हैं। और अगर हमारा बड़ा होता जा रहा है लॉस तो मतलब गलत जा रहे हैं, तो फिर हम चेंज करेंगे डायरेक्शन। तो वो कौन बताता है हमें, मतलब गाइड कौन करता है? जैसे अभी संजय तुम लोगों को गाइड कर रहे हैं, ऐसे कौन गाइड करता है उनको कि भाई इधर गलत है इधर सही है? वो करता है हमें ग्रेडियंट, ठीक है। तो वो जो है डेरिवेटिव करता है कि इधर तुम्हारा साइन सही जा रहा है, ठीक है, इधर तुम्हारा ग्रेडियंट जो है बड़ा हो रहा है, इधर तुम्हारा छोटा हो रहा है, तो वो गाइड करता है, ठीक है। अब ये एक्टिवेशन फंक्शन क्या करते हैं तुम्हारे उसमें, उसको फाइंड करते हैं कि हाँ इसमें वैल्यू तुम्हारी नॉन लीनियरिटी आ रही है कि नहीं आ रही है, किधर जाना है, जीरो के जाना है, ये वन के बीच में जाना है। अगर आउटपुट लेयर में लगा रहे हैं तो मल्टी क्लास, अभी जैसे किसी ने पूछा था, तो उसमें कई सारी प्रॉबिलिटी वैल्यू हो जाती हैं, उनके बीच में कैसे प्रॉबिलिटी फाइंड करनी है, राइट। मतलब क्लासेस को डिवाइड कैसे करना है, 5 क्लासेस हैं तो 10% ये हो गया, 20%, हर एक क्लास को थोड़ा थोड़ा प्रॉबिलिटी दे देते हैं, ठीक है। तो ग्रेट सेशन। और कोई कन्फ्यूज़न है या क्वेश्चन है मेरे लिए या संजय के लिए या किसी और के लिए ग्रुप में?
सर जो एक मिनट मैं एक फाइल शेयर करना
श्योर
चाहूंगा।
श्योर श्योर।
सर ने एक्सप्लेन किया ग्रेडियंट्स का, I'll just keep it a very small one. Like हम जो वेट्स, जो भी हमें पैरामीटर को हमें चेंज करना होता है ना, we want to get update we want to update the weights. we use this a very classical formula, which is of gradient descent. Like whatever parameter we want, a new parameter is equals to old parameter minus some learning rate, and this is the gradient we are talking about. This is the gradient we are talking about. So what happens is, like, since it is an iterative process, it goes on calculating gradient, and we get some new value. So what we are doing is, like, we try to come up to some very global minima actually, for where the loss is very minimized. For जैसे यहाँ पे दिख रहा होगा, for this, if we compute loss versus the parameter W1, for this W1 dash, the loss is very minimal. बहुत कम loss है, right? So actually, अगर हम let's say कि initial our W1 was something here, we calculated this, हम यहाँ पहुंचे again. At this point, we try to compute the gradient, we get there, and so on and so forth. What will happen is, after some iteration, we'll come up to a very minimal value of W, for which the loss is minimized. This is what sir was telling. So like for every process, we have this gradient, as I have talked about. So यहीं पे यही चीज सर ने बताया था कि this is the gradient we are interested in calculating, and based on this, the value of gradient we are getting, you can either get a very small value, let's say like for sigmoid function, as somebody has asked कि हम कब इसको use करेंगे, या फिर how it works against this ReLU. The gradient is very close to 0.25, and then you compute, you multiply it with your learning parameter alpha. That is also a very small value. So ultimately, your final value is very less. And ultimately, in that case, what would happen is, just a second. What would happen is this this value alpha times the gradient, it is 0 or very close to 0. So essentially, your new parameter is nothing but the old parameter itself. So technically, आपने learning किया ही नहीं, आपने model update parameter को update किया ही नहीं. This was vanishing gradient problem. Another one was exploding gradient problem. ये भी सर मैं बस एक मिनट लूंगा, इसको भी डिस्कस कर लेते हैं.
Definitely.
Let's say we are starting here, and let's say the gradient is too large. So what would happen is, if we again plot this parameter W as compared to the loss, we would only iterate in between this curve, and we would never be able to come up to this global minima. हमारा जो step size होगा, जितना में step आगे बढ़ना है या पीछे बढ़ना है in this curve, we would not be able to converge to this W dash, for which the loss is minimal. This was the problem with exploding gradient problem. So I guess I have explained this also, sir.
Awesome. Yeah, so let's conclude this कि हमें रिलू के जगह पे स्विच क्यों यूज़ करना है. सो बेसिकली हमारे रिलूज़ में कुछ प्रॉब्लम थे, ठीक है, कि वो मतलब जैसे एक कम्युनिटी में एक फ़नी चीज़ कही जाती है कि बी लाइक रिलू इन रियल लाइफ. क्यों? क्योंकि वो इसलिए कहा जाता है क्योंकि वो हमेसा पॉजिटिव रहता है, ठीक है. वो मतलब जितने भी निगेटिव चीज़ होती हैं उनको हमेशा कन्वर्ट कर देता है जीरो में, ठीक है. वो निगेटिव में जाता है. तो दैट्स व्हाट लाइक या इन रियल लाइफ आई मीन पीपल सेज लाइक बी लाइक रिलू. ओके, सो वहाँ पे वो इश्यूज़ थे, इससे याद रहेगा तुम्हें. और उसके अलावा फिर हमारा जो है मतलब कई सारे इश्यूज़ थे उसमें, थोड़े बहुत कहीं पे यूज़ भी हो सकता है रिलू. बट ये इन्होंने क्या किया स्विस वालों ने कि इन्होंने गेटिंग मैकेनिज़्म दी और स्लाइटली निगेटिव वैल्यूज़ को भी अलाउ किया, और ये शार्प मतलब ये स्मूथ हो जा रहा था कई जगह पे, ठीक है. तो उसकी वजह से फिर इन्होंने यूज़ करना स्टार्ट किया. एंड कंक्लूड इट मे बी संजय, कंक्लूड इट इन योर वर्ड्स, 2-3 lines, then let's wrap it.
I guess that's it from my side. Like,
thank you for everyone joining, and let's meet next week. जैसे शक्तिमान का शो आता था, नेक्स्ट वीक, ठीक है.